Alright folks, so today we're going to talk about blocking in a little bit more detail. So let's go ahead and define some stuff. So first of all, an experiment that involves blocking is called a randomized block design. Oh, there we go. And it basically works how we kind of mentioned before. Where you have subjects that are separated into groups, which are called blocks, based on some kind of characteristic that we think might affect the results of the experiment. So let's write that down. So subjects, or units, experimental units if you're not using people. Are separated into blocks. Based on a characteristic that might affect the experiment. Then once you have these blocks separated, then you do random assignment of treatment within each block separately. So then treatment is I keep doing that. So then treatment is randomly assigned within each block. There we go. Okay, so that's what block design looks like, and so we're going to look at a couple of examples that are going to ask you some more specific questions about blocking. So our first one goes like this. So it says, Instagram is considering using a new interface designed to be more user-friendly. Their hope is that the new interface would encourage more people to use Instagram. The company recruits 150 volunteers to try out the new interface. They would like the volunteers to simply try posting a video from their phone on their story using either the new interface or the old one. Of the volunteers, about 90 of them already use Instagram on a daily basis, and the other 60 do not have an Instagram account or do not use it regularly. In this case, why would blocking be an essential element of this experiment? So in this case, we're going to talk about blocking, but basically what they're asking is, all right, I have 150 total volunteers. Why don't I just, at this point, randomly assign treatment to them? Meaning, why don't I just randomly assign half of them to use the new interface and half of them to use the old interface and call it a day? And so why would blocking be a better choice than just randomly assigning treatment right off the bat? So you can pause this, kind of discuss for a second, write down an idea, and then we'll continue in just a little bit. All right, so here's sort of what you should have come up with to some extent. So the deal is this. If we randomly assign treatment, so if we randomly assign half of these 150 volunteers, 75 of them, to use the new interface and 75 of them to use the old interface, then what could happen by chance, now it probably won't, but it could happen by chance, is you might end up with the group using the old interface or the group using the new interface is all purely Instagram users only, or all purely non-Instagram users. So I went with an example where the group in the new interface was non-Instagram users. So I said in this case we would want to separate the group by those who already know how to use the current Instagram and those who don't. If we don't do this, it is possible that by randomly assigning treatment, the new interface group could be made up of mostly people who don't use Instagram. So think about that for a second. So this is where I stopped writing at this point. So for a second, So if we're trying to test a new interface to see if it's better than the old one, and we have a bunch of people who don't use Instagram anyway, they may have trouble just using the new interface for Instagram because they're bad at Instagram. They don't know how to use it. And so in that case, this is where I keep going. In that case, the new group might not be able to upload the video, and the experimenters would assume the new interface was bad when maybe those people just didn't understand Instagram at all. The experimenters, would not be able to tell if the new interface is better than the old. So basically what we don't want to happen is we don't want the non-Instagram users to mainly end up in one treatment group. And so what we could do instead is we could separate the group into the 60 people who don't have an Instagram or don't use it, and 90 who do. And then within those groups, we can administer treatment to each group. So for example, if both the already doing Instagram group and the newbie group, if in both groups the new interface seems to work better, then the experimenters can definitively say, yeah, the new interface is better. So that would be an example where blocking would be a good idea, because I know that if one of these groups of people ended up in one treatment group, that would cause confounding. Okay, so now we actually move on to a really interesting form of blocking. And this actually kind of goes into the last example. So the question is with Instagram, and by the way, hopefully you guys knew this, but maybe you didn't. By interface, they just mean what Instagram actually looks like. So when I go into Instagram, how do I know where to upload videos? What do I need to press? Like that kind of thing. So in the previous example, we just want to know if the new interface is better than the old interface. And so a way that we might actually be able to test that is we could have each of the volunteers use both and see which one is easier for them. Well, that actually is a type of experiment, and it has a name, and it is called, it is called a matched pairs experiment. And it basically looks a couple of different ways, but it goes like this. So matched pairs design is a specific type of blocking. And it can look two different ways. So way number one is you match together pairs of experimental units that are similar and give one of them one treatment and the other another treatment. So the way that might look in the previous example is I would pair up each of the Instagram users and each of the non-Instagram users, and one of my people in my pair would use the new interface and one would use the old one, and I would basically compare who did a better job or who uploaded a video quicker or whatever. So the first way to do this is to match together two, oh my gosh, experimental units that are similar and give one a treatment and the other a different treatment. Then I would compare each pair. So I would give one person in the pair one treatment, one person in the other pair another treatment, and then within that pair I would compare them. So if I had a total of 60 people who've never used Instagram before, I would put them into pairs of 30, so there would be 30 different pairs. And for each of the 30 pairs, I would say, okay, who did a better job, new interface or old interface? So that is one way to do matched pairs. The second way to do matched pairs is to basically give one subject, one unit, two different treatments in a random order. So, or option number 2 is give one experimental unit two different treatments. Oopsie. In a random order. And then you compare results. So what that would look like in this case is each of the 150 people would try both the old and the new interface. And some of them would try the old interface first, some of them would try the new interface first. And we'll talk about kind of why that happens in a little bit. And then you would just basically compare for each person. So you would essentially have 150 different results that compare the new and the old interface. And so for each person, it would be like, oh yeah, the new interface worked better, or half of them said new, half of them said old, so it doesn't really matter, something like that. So in a matched pairs design, essentially you're giving one person or one unit two different treatments and comparing those treatments on that one person. This is a really awesome design if you can get away with it, because if you're giving each person a different treatment, then basically the only outside factors you need to worry about are just the order of the treatment, because I'm individually testing this experiment on a bunch of different people. So for example, in just a straight up blocked design for the last example, I need to control the fact that some of these guys have used Instagram before and some haven't. Well, the way to control that is by blocking. I can split up my group, or if I just do matched pairs, then I've already kind of controlled for that anyway. It's already done. I don't have to worry about that. So matched pairs is kind of a cool design in that respect. So let's check out kind of an example. All right, so it says researchers want to test whether chocolate affects blood flow in the blood vessels. The researchers recruited 17 healthy volunteers and want to see if there's a difference in blood flow when the volunteers eat both bittersweet chocolate and fake chocolate. So for part A, they want you to describe a matched pairs design for this experiment. So not a blocking, but a matched pairs design. So let's kind of talk through this generally, and then I'll have you write up something, and then we'll compare it to what I wrote up. So in a matched pairs experiment, essentially what I want to try to do, if I can get away with it, is I would like each person to have two different treatments. And so in this case, they want to test the effects of chocolate on blood flow. And they want to test, in this case, our two treatments are bittersweet chocolate and fake chocolate. So I don't really know what fake chocolate is, but we're going to go with it. That being said, so I have two different treatments, bittersweet chocolate and fake chocolate. So what I want to do is I want to make sure that each person eats both, and then I want to test their blood flow and see if the blood flow is better with the fake or with the real chocolate, or if there's any difference at all. Sorry. So here's how we're going to do that. I know that for matched pairs, I have to give two different treatments in a random order. So I want to make sure to, first of all, give these two chocolates in a random order. So each person will take or eat the chocolate in a different order. Okay, so that's one thing I need to write about. Next, I need to give them the next thing. So I would, I don't know, do something like flip a coin maybe to see which chocolate they get first. And then after that, I would need to measure their blood flow in some way. Then maybe a week later, I wouldn't want to do it like in the same day, because I don't know how long the effects take to wear off, if there are any effects. So then maybe later the next week, I would have the next person, or I would have the person take the next type of chocolate. And then again, measure their blood flow. And then finally, in the end, I should have two different blood flow readings. I would just need to compare them for each person. So pause this for a second, write down kind of a description of how that would look, and then we can compare it to mine. Okay, so hopefully you came up with something like this. So it says, have each of the 17 volunteers flip a coin. If the coin is heads, then they eat the bittersweet chocolate on one selected day. Tails, they eat the fake chocolate first. Then, 1 week later, have the volunteers eat the other type of chocolate. After each treatment, measure blood flow. Finally, take the difference in blood flow, bittersweet minus fake, for each subject. So this is the kind of detail you want to see you want to say if you're asked to describe a matched pairs experiment. So if you flip your paper over to the back, they're going to ask you a couple of other follow-up questions, so let's look at those. All right. So it says, why is a matched pairs design for this situation better than a completely randomized design? And remember, a completely randomized design just means an experiment where I randomly assign treatment. There's no blocking, nothing fancy, nothing else. So take a second, pause this video for a second, talk to your group. Why do you think in this case a matched pairs design for this situation would be better than just a completely randomized design? So pause this and then we'll chat. All right, so hopefully you came up with something like this, but why is a matched pairs design for this situation better than a completely randomized design? So in a completely randomized design, you got 17 different people who might all react differently to chocolate. You don't know anything about these people. They're volunteers. They could have weird health issues. Some of them could naturally just have better blood flow. Some of them could be, I don't know, unhealthy and near death. You don't know. And so in a completely randomized design, you could end up with people who have just kind of naturally faster, stronger, I don't know, blood flow in one group. Whereas with matched pairs, you're just comparing each person to him or herself. And so with matched pairs, any kind of weird characteristics that might mess with your experiment are accounted for because each subject is only compared to him or herself. So that's pretty much what I wrote, as you can see. I know you might have gotten crazy detailed. You could have. What I wrote is perfectly acceptable as well. So in a completely randomized design, the different characteristics of the volunteers might affect their response to the chocolate. With matched pairs, those characteristics are accounted for since each subject is compared only to him or herself. Just kind of a side note for the AP test. When you're asked to explain why something is better than something else, so why is matched pairs better than completely randomized design, a good rule of thumb is to talk about what would be wrong with the thing that they're asking you to compare to. So what's wrong with a completely randomized design, and then also mention what's good about a matched pairs design. So in my case, I talked about, hey, the reason why it's better is because in a randomized design, this could go wrong, versus in a matched pairs, this could go right. So that's kind of a good rule of thumb when you're actually answering questions on the AP test. Give a couple of different reasons. Don't just focus on the negative of one or the positive of the other. Include both. Okay? And then finally, for this example, the last question is, why is it important to randomize the order of the treatments for these subjects? So you can take a couple seconds. I will give you a hint before that, and then you can compare your response to mine. But we actually saw a question like this that had to do with chocolate and blood flow. And in that case, they said that they did an experiment, and on the first day, they measured blood flow of a bunch of people. And then a week later, they gave the people chocolate and then measured their blood flow again. And they said that every single person's blood flow improved, basically, on the second day. So in this case, you may or may not remember this question, but they basically did a matched pairs design, but they didn't randomize when these people got treatment. So everybody got basically fake treatment or no treatment on the first day. And then a week later, everybody had chocolate on the second day. And the question that they asked you is, why are you not able to conclude anything? So that's sort of my hint as to why is it important to randomize the order of treatments for the subjects for this example. So kind of try to remember that problem, think about that, and then write a response, pause the video, obviously, and then resume when you're ready to compare your answer to mine. Alright, so why is it important to randomize the order of treatments? So we don't know what outside factors could affect the results of the experiment. For example, on the second day of treatment, it might be warmer outside, improving all of the volunteers' blood flow. And we might mistakenly think that the chocolate administered that day was effective, when in reality, we don't know if it was the chocolate that was effective or if temperature just caused an improved blood flow for everybody. So by randomizing the order of treatments, we prevent, hopefully, we should prevent, all bittersweet or fake chocolate from being administered on the same exact day, and then we would avoid a situation kind of like the one I just described. So in that case, that's why it's important to randomize the order of treatment. So it's always important generally to randomize order, because in doing so, you're going to even out outside factors that could affect your experiment. Okay. All right, folks. So to kind of round off experiments, we have talked about a bunch of different types of experiments. And so now we're going to chat really briefly about, okay, I did my experiment. I did it a good way. I got reliable results. What am I allowed to actually infer? What am I allowed to actually conclude from experiments? And what am I allowed to conclude from observational studies? Because it's not necessarily nothing. So first of all, statistically significant results. We're going to spend the whole second semester when I'm back talking about statistically significant and what that actually means in way more detail than you've ever wanted to know. But for now, what you need to know is this. If you have an experiment or a study with statistically significant results, this means that your results were so extreme they could not have happened by chance, or they probably did not happen by chance. So let's write that. So this means your results were so extreme that they couldn't have happened just by chance. They probably couldn't have happened just by chance. So for example, if I was trying to do an experiment where I wanted to see if people could taste the difference between tap water and Edison drinking fountain cockroach water. Let's say I did an experiment, and listen, if you can't tell the difference, then about 50% of my volunteers should be able to tell which type of water was tap water, and 50% shouldn't be able to tell. But if there is a difference, which actually this was an experiment somebody did last year, and there certainly was. But if I did my experiment and 96% of people were able to accurately identify which type of water was tap water versus Edison cockroach water, then that's pretty significant. I'm expecting to have about 50% of my volunteers be able to tell the difference, and I had 96% be able to tell the difference. That's an extreme result. That's extremely far away from the 50% that I was expecting. And so in that case, that's going to mean that I have statistically significant results. And so here's the main spiel. If your results are statistically significant, then you get to conclude some stuff as long as the following have happened. So if your results are statistically significant and you have performed an experiment that is well designed, you can, depending, conclude that the treatment caused the response. So you can conclude the treatment caused the response. Okay? If you have statistically significant results and you used a random sample to gather your data from a population of interest. So you used a random sample, not random treatment. This is not talking about an experiment. So this guy is not an experiment. This is an observational study. So if you used a random sample from a population of interest, you don't get to conclude causation but you can generalize your results to the whole population. Oops, let's spell that right, shall we? So if you did take a random representative sample, then you can generalize your results to the appropriate population. And if you used a random sample and you performed an experiment and your results were statistically significant, you, my friend, can conclude that treatment caused the response, and that this is true for the whole population. Otherwise, so my last little spiel here, and then we're done. So in the last case, if you use a random sample and perform an experiment, you can, if your results are statistically significant, conclude treatment caused response, and you get to say that this is true for the whole population. If you just performed an experiment, the only people who you can say this is true for are people like the people who were involved in the experiment. So if you performed an experiment, this is only true for people who were like the people who volunteered for the experiment. So this is only true for similar volunteers. Versus if you took a random sample, you can say this is true for, or random or representative sample, you can say this is true for the population that they're representing. So that's kind of cool. All right, people, chapter 4 is donezo. Good luck.